We begin this next section by looking at induced EMF and magnetic flux. So we've talked about in previous lectures how electric current can create magnetic fields. That the idea is that when current goes through a wire, the moving charges generate magnetic fields. All moving charges generate magnetic fields. But the opposite is actually true as well. Magnetic fields can cause charges to move. They can induce current. So magnetic fields can create current when magnetic fields are manipulated in certain ways, and we're going to talk about that in this chapter. So the process of creating EMFs, right? An EMF, electromotive force, is just basically a way of generating current. Batteries produce voltages, EMFs across them. Generators can produce EMFs. So for current to flow, the potential at two ends of a wire have to be different. That is an electromotive force, that's an EMF. That potential difference is an EMF. So magnetic fields can create current by generating EMFs, which then, of course, create potential differences that cause current to flow. When we do this with magnetic fields, when we generate EMFs with magnetic fields, we call that process induction. We induce a current. Because magnetic fields, again, are these invisible lines, this weird, spooky action at a distance, we are not, like with a battery, physically connecting up a circuit to drive current through that circuit. Magnetic fields can produce current in wires that are not connected to anything. So it's not just a magnetic field that creates the EMF. Specifically, it's the changing magnetic flux. And we haven't really talked about flux yet, and we'll introduce that in a moment. The magnetic flux is used by the symbol psi sub b. So we have capital Greek letter psi circle with a bar with two ends, like a barbell, a vertical barbell. I added the subscript b there to talk about magnetic flux. In physics, you can also talk about electric flux. We haven't really talked about that. Your book doesn't make that distinction, so it just uses a psi. This is the amount of the magnetic field that passes through some area A. That's what flux is. It's the amount of magnetic field lines that pass through some area. So it's not just the magnetic field that we have to worry about. It's how much of the magnetic field is inside some area that we're interested in exploring. So an analogy would be, imagine it's raining. So the raindrops are coming straight down, so the direction of the rain is downward. And I have a big hula hoop. Now, I can change the amount of rain that goes through my hula hoop, right? I can have the hula hoop where the surface is horizontal, so that the ring is around this way. I get maximum amount of rain passing through the hula hoop. As I turn the hula hoop and I put it at some angle with respect to the direction of the rain, a vertical hula hoop, or say where the surface is oriented vertically, no rain passes through the hula hoop. It passes in front of and behind, but the area in the middle gets no rain passing through it. So that goes from a maximum rain flux to zero rain flux through that area. Now, instead of rain, imagine it's magnetic field lines. So in this case, I have magnetic field lines pointing down, and I'm looking at again, a ring of area A. I can change the amount of magnetic field lines that go through that area by changing the angle between the normal to the surface and the direction of the magnetic field. When they're parallel, when the surface normal, is up or down, is parallel or anti-parallel to the direction of the rain, I get a maximum magnitude for the flux passing through that area. When they're at 90 degrees from one another, when the hula hoop is oriented like this, the normal to the surface is pointing horizontally, the rain or magnetic field lines are going vertically. At 90 degrees, we end up with no magnetic field, no magnetic flux through the area. So it's cosine dependent, right? When this is zero, when they're parallel, you get maximum magnetic flux. When the cosine is 90 degrees, cosine of 90 degrees is zero, you get no magnetic flux. So the magnetic flux through some area depends on three things. It depends on the strength of the magnetic field, right? no magnetic field lines, no magnetic flux. If I draw in more magnetic field lines here, I create a stronger magnetic field, the flux will go up because I'll have more magnetic field lines going through that area. It depends on the area itself, right? A big area, it's easier to capture more magnetic field lines than in a small area. So that changing the area can change the flux. And then finally, this angle cosine of theta can change the flux. So the three ways of changing the magnetic flux: change the strength of the magnetic field, change the area of the loop that you're looking at. So it's a loop of wire. Let's imagine it's made of sort of a flexible, almost like a slinky-like wire that can shrink and expand. Well, then if you have a loop of wire that shrinks, you're changing the area, which changes the flux. Or you can rotate the loop. By spinning the loop, you change the amount of magnetic field lines going through the loop because you change the angle, and that can change the magnetic flux. A changing magnetic flux generates an EMF. So if I want to change this with time, there are three ways of doing it. I can change the magnetic field strength with time, I can change the area with time, or most easily, and what's used in motors and generators, I can change the angle with time.
Hello, I wanted to demonstrate the idea of how a changing magnetic flux can actually generate an electric current. So to do that, I have with me a galvanometer. So if you recall, a galvanometer is simply a device that measures either voltage or current depending on how you have it set up. It's not a digital but an analog device. It has three built-in settings, 1, 2, and 3, that align with three internal resistors that will measure the current. So if current passes through between the black lead here and the red there, the current, the needle will move in one direction or the other. So I'm going to set that up. I'm going to plug this in with wires, and those wires go to a simple loop of wire. So this is very finely, very small copper wire, slightly insulated. So the copper wire has to move through the wire, not across the wires. And there are 3,200 turns of copper wire here. So a lot of different turns, a lot of different loops of copper wire attached, again, by wires. This is the only thing that is attached to the galvanometer. There's no battery in this system at all. There's no system, chemical or electrical battery that can generate a current. It's simply wire and a galvanometer. Now I'm going to use a simple bar magnet. So this is a simple bar magnet. It has a north and a south. So again, imagine magnetic field lines coming out of the north end of the magnet, looping around and coming back in the south. So there's a spray of magnetic field lines coming out this way, circling around above and below the magnet, in front of and behind the magnet, all coming back together to converge on the south end of the magnet. And then those magnetic field lines go through the magnet and spit back out the north. Again, magnetic field lines loop around. So I'm going to simply take this magnet, the north end of this magnet here, and put it through the loop of wire. So you can see this little area A in here, little square. You see my hand behind it. That little area inside the loop of wire is where this magnet is going to go in. So from the side, right, this is what it will look like. The magnet will go approach and move away from that area. So magnetic field lines, again, these invisible lines coming from the end of the bar magnet, imagine them going into and then getting pulled out of this loop of wire. So I only have two hands, and so I'm going to put the loop down on the side here. I'll have the magnet, you'll see my hand move up and down. That's where it's going in the loop of wire. And I'm going to show you the galvanometer. I'm going to push the button for the second, and watch what happens as I simply move the magnet down through the loop of wire. The needle jumps to the right, and then when I pull it out, the needle pulls back to the left. This is inducing a current. I'm forcing current through the wire just from my mechanical motion. Faster I go, the more current I get. Slower I go, the less current that appears. But it's the motion that generates the current. So if I just put the magnet in and I keep it still, notice that no current No current is generated. It's only when I move it is the current generated. So the area here isn't changing. Area A isn't changing. The angle between the magnetic field lines and the magnetic field isn't changing. So what's changing is the amount of magnetic field lines going through this area. The strength of the magnetic field in area A is changing with time, which generates a current. If I could somehow change the area, if I could stretch out this loop and pull it back together, that would also generate a current. Or if I turn the magnet, that should generate a current as well, although I can't demonstrate that. Again, I don't have 3 hands. That'll generate a current in the galvanometer. So that's electromagnetic induction, and it was discovered kind of by accident. So the idea was Michael Faraday was doing demonstrations to the public and had some electrical equipment out for demonstration purposes, had some magnets out for demonstration purposes, and noticed when a magnet was moved near a coil of wire, the galvanometer moved. So it was just dumb luck initially that allowed us to see the connection between magnetic fields and electricity. We now know the two things are intimately related. They're two sides of the same coin. And we call this the electromagnetic force. And we're going to explore this more in this chapter.